Hi. So today I'm going to be talking about this idea called expectation of linearity. So what does this mean? So a lot of times you require an order of n solution while coding, but you have with you an O of n square solution, right? But you really want an O of n solution. So you like sort of submit this O of n square solution and hope or expect that they only ask test cases for the linear solution, and which is a fair thing to do. It's not like they're looking for the worst possible test cases to like make your code fail or something. So this is completely reasonable uh, for you to do. So this is called expectation of Okay, fine. No. This is not what you're talking about. There's no such thing as expectation of linearity. I don't know how well that joke went, but we're talking about linearity of expectation today. Um, okay, so this is one of the ideas I was quite confused for a long time. I feel less confused and therefore justified in making a video. So what is this? Before we even talk about, like, we're going to define all of these terms, that's fine. But we'll have to define a few more before I define what linearity of expectation is. This whole thing first has something to do with these things called random variables. And random variables are variables. That means they can take up many different values, and they take up each of those values with a probability. So in particular, we're going to be talking about discrete random variables. Let me just check that it's recording after all this. Okay, good. And that I'm sharing screen. Okay, great. Yeah. So we're going to be talking about discrete random variables. Okay. So an example I can like I said, they take up different values with different probabilities. So an example could be X. It takes up, say, the value 0 with probability half, the value 1 with probability 1/4, and value 2 with probability 1/4, right? This is the, let's call our random variable with capital letters like X are the values they take up with little x, and the probability is P of X. All right. Okay. So if you have a random variable, you know the values it takes up, the probabilities with which it gets taken up. Okay. Once you have this random variable, you can do functions of random variables, which are new random variables. So you can, for instance, define f of x equals 2x, right? Which is a random variable in itself. So the so just to like make a table, like if the x was the previous x that we used, yeah. So let me call this. I don't want to call, okay. These are the values f of x takes up, and these are the values x takes up, and these are the probabilities with which it's taken up. So we said x was 0 with half, 1 with 1/4, 2 with 1/4. And so f of x takes up the value 0 with probability half, 2 with probability 1/4, and 4 with probability 1/4, right? So this is a new random variable, like also has values and also with certain probabilities. All right, so you can define these random variables, and you can define functions of them. What is expectation? So the expectation of a random variable f is we are making a statement of all its values and the probabilities they take up. So we're saying this is equal to sum over, and this is a little bit abusive notation, but I think it's clear what I'm doing, sum over x times P of x, right? So the value times the probability it takes up. So in our particular case, for example, expectation of the above function, let's say f dash, expectation of f dash was, oh, sorry. This should be f of x, right? The E of f is, yeah, the value it takes up time, the value of the function times the probability with which it occurs, right? Was 0 with probability half, plus 2 with probability 1 over 4, plus 4 with probability 1 over 4 equals half plus 1 equals 3 by 2, right? Yep. So that is expectation. Okay. And yeah, maybe, like, I don't know if I should have structured this differently, too many definitions first, but hopefully you've seen something similar before, and when we do problems, it'll all be relatable. And now, what is linearity of expectation? It's a property that expectation takes that is a statement of, like, let's say there's an underlying random variable x, okay, and two functions of this random variable, f of x and g of x. Then what the statement says is, if you have alpha, if you're taking the expectation of this new random variable, alpha times f of x plus beta times g of x, right? It's the same as alpha times expectation f of x plus beta times expectation of g of x, right? And in particular, which is the case we'll care about most, is where we don't think about alpha and beta. Basically, expectation of f of x plus g of x is expectation f of x plus expectation g of x. Now, written this way, this is actually very, very easy to see, right from um, uh, the definition of expectation, because if I have expectation of, and you can add the alphas and betas, the same thing holds. It's the same, whatever the proof I'm writing here works. But expectation of this is basically sum over x, f of x plus g of x times probability of x, right? Which I can split up as plus sum over x. I should really x small x, right? G of x. And maybe I should make clear that f of x, no, I think this is fine. Yeah. P of x, and this thing is just expectation f of x plus expectation g of x. Yeah, so that's it. I just distributed this and I get this, right? And it's also easy to, like, there's a nice way to visualize this as well. If you plot a graph with the probability measure on the x-axis, so for example, you can take, say, your random variable takes 3 values, x1, x2, x3. You could, plot the probability of x1, probability of x2, and probability of x3, right? And maybe this is f of x1, f of x2, f of x3. So f of x1, f of x2, f of x3. Then this area is basically the expectation, right? Right. And you can see that if you sort of had another function, if you had like g, here, where g of x1, g of x2, g of x3, And then f plus g would, just be adding up both the areas, which is exactly what we did. It's nothing different. But for me, like what was okay, so yeah, if to make it clear, what I'm saying is if you had, then you could write down f of x plus g of x, f of x1 plus g of x1, f of x2 plus g of x2, and f of x, plot these guys as well. X3, and the area of this big plot would be the sum of the areas of the other two plots, which is what we were seeing. And it almost seems like very, very obvious when you say it this way, but usually, like, I guess for me, like sometimes you see linearity of expectation written as like there's two random variables x and y, and expectation of x plus y equals expectation of x plus expectation of y. And you can still prove it like very similar to this and it holds. But when you see this immediately, you're like, wait, how does this hold all the time? Like, don't you care? Like, what if even if they're not independent, like, so it didn't seem very obvious to me at first. Like you just take two random variables and you can add up their there's this expectation of their sum is the sum of their expectations, and you don't need to worry about independence. But the key, like at least to make it clear for me, is always think of just one underlying random um, variable, right? So you can always think of, like when you see a statement like this that says expectation of x plus y is expectation x plus expectation y, you can always think of x as being x of some random variable omega, and y as being some y of some random variable omega. And omega could just be the tuple x comma y, right? That has both of the values, and the random variable x could just be picking the first element, and the random variable y just be picking the second element. And now the same thing holds. So we know that expectation x of omega plus y of omega, just like before we saw, is equal to expectation x of omega plus expectation y of omega. Okay. Um, so I don't know if I was able to convey my confusion for some time, and then like seeing that it's clearer when you just think of it as one underlying random variable. But hopefully it should definitely get clearer when we do the like basic problems that linearity of expectation is used for. And as you can see, this usually we use it in the cases where you're trying to compute expectation of some function. By itself, it seems like a difficult task, but you can split up the function into sum of a few functions each of whose expectation is very easy to compute. Okay, and we'll look at an example now. And this idea of like, okay, what is the underlying variable and what is the function of that? What is the underlying random variable? What is its function and what is the functions we're splitting up into? That was like useful to think about. Okay, so the first problem that we'll do is called the n-hats problem. Okay, so what is the n-hats problem? So it's like n people maybe went to a restaurant. Each of them wore hats, and they all hung their like hats before eating. They came back, and they all just took a random hat. It was all shuffled. And if every possible shuffling was possible, like with equal probability, and each of them took their hats back, what is the expected number of people who get their same hat, right? Okay, so it's not, at least it's not immediately easy how to think about this. So maybe I'll write down the question. So how do I write this succinctly? Maybe n hats shuffled in random order, expected number of people who get their hat back. Okay. So to do an example, suppose you have 5 hats, right? And let's say initially first guy has his hat, second guy has his hat, 3, 4, and 5. 5 guys have their own hats. It was randomly shuffled, and now it's 5, 2, 3, 4, 1, right? So for this shuffling, right? In this shuffling, 2 guys got their hats back. So for this shuffling, 2 guys got their hats back. So here the random variable is basically, we don't know the ordering in which when the n people come back, we don't know the ordering in which they'll see their hats, right? So that ordering is the random variable. And how many different values can this random variable take? Well, how many shufflings are there? There are n factorial ways in which these hats can be shuffled around. So you have a random variable, say x, which is a sequence x1, x2, and so on, xn, and it takes n factorial values, right? And we're assuming, the question assumes that each of this happens with the same probability, like there's equal chance of every shuffling happening. So n factorial values, each with probability 1 over n factorial. Okay. And the function that we're computing, okay, of this random variable is f of x, which is f of x1, x2, and so on, xn, right? Is equal to number of, maybe I can write, to write this, we can say this is the cardinality of xi of this set. I mean, maybe this is too complicated, but okay. Xi such that xi equals I, right? So, for example, in this case, when I said f of this shuffling, 5, 2, 3, 4, 1, of 5, 2, 3, 4, 1 is 2, because 2 guys are at their same spot, okay? So now we know our random variable. We know the function of the random variable that we're computing. And our job is to find the expectation of this function, right? We know the function is for each of the sequences, like the number of hats that are whatever, equal at the same position. And now we want to compute expectation f of x. And now suddenly this seems like a tall order, right? Because there's n factorial guys, possible sequences. And in each of them, you need to compute how many hats were given, were there. And I mean, were in their right positions, and multiply all of those and add them, right? So yeah, here is where we try to do linearity of expectation. Okay, the function we wanted to compute was this. Can we break it up into smaller functions? And I mean, I definitely, I don't think I would have thought, I mean, this is a very standard problem. So like, I guess you see it and you think about other problems, but even if I know linearity of expectation, I won't come up with how to break it into like these particular functions, I think, unless I'm used to like indicator functions and things like that. But yeah, just saying after having read solution. Okay, so yeah, so now let's look at this case. Okay, so we have this function f which we want to break up. So f of 5, 4, I mean, let's take an example case. This, okay, let's just say x1, x2, x3, x4, x5. Okay. What I can do is I can break this up into f equals f1 plus, of each of them being functions of capital X, by the way, plus f2 of capital X and so on, fn of capital X, where f1 just asks is 1 if x1 equals 1, 0 otherwise, right? And same thing here. F2 is just 1 if x2 equals 2 and 0 otherwise, right? So I can break it up into functions like this and like maybe take a minute to see that these are indicator functions because they only take values 1 and 0. And yeah, they only take values 1 and 0. And we can see that this adds up to the whole function. And we can look at our example of f of phi. What is that again? Phi 2, 3, 4, 1. Right? So here I have f equals f of x equals f1 of x plus f2 of x plus, let me write the whole thing, f4 of x plus f5 of x. And f1 of x is 0 because that's not in its position, plus 0, plus 1 because that's in its position, plus 1, plus 0. So this is 2. All right. So this is a nice way to split it up into functions. And for different problems, it's not like, maybe it takes a little thinking how to split it up into functions. And so why did we do this? Like clearly, like each of the expectations of these functions should be easy to compute. Is it easy to compute? Let's see. Let's try to compute. So now we want, to recap, we want expectation f of x, and we're going to be doing f1 of x plus expectation f2 of x and so on, right? And we are claiming this is easy to compute. Okay, let's see if it is easy to compute. How do I compute this? So I have all of these n factorial sequences, right? N factorial sequences. And some of them will have 1 in the first position, and some of them won't, right? So with what probability do I have 1 in the first position? So clearly, the way I can count the number of guys that has 1 in the first position is fix that and then permute everything else, right? So n minus 1 factorial. So n minus 1 factorial of the guys over n factorial of the guys will have 1 in the right position. So this is 1 over n of the guys, right? So the expectation, so the probability of having 1 is 1 over n. So expectation f1 of x is basically 1 times 1 over n, right? Having the probability of getting 1 in the first position times the function, plus 0 times n minus 1 over n, right? Which is 1 over n. Okay. So computing expectation of f1 of x is easy. And since there's nothing different from one than the other positions, by symmetry, it holds for every other position as well. So each of the expectations are 1 over n, right? So then you just add 1 over n plus 1 over n and so on n times, and you get expectation f is equal to n times 1 over n equals 1, right? So that's the answer. So if a lot of guys go and randomly shuffle their hats and each one takes a hat back, the expected number of guys who get their hat back is 1, exactly. Although, yeah, like it's, then I see expectation is like a mathematical definition, and like, I guess, yeah, you can redefine what you mean by when I say how many guys do I expect to get their hat back, I should be thinking like, oh, I mean sum over x, f of x, p of x. But it doesn't always, like, it's not always the intuitive meaning of expectation is what this is. But yeah, mathematically, the expected number of guys to get their hat back is 1. Okay, cool. So that was one example. I'll probably do another easy example. So this is the n balls and m bins problem. Okay. And I'm sure there are many problems, and this is not the n balls and m bins problem. I'm sure many such problems exist. But the problem we'll be asking here is there are m bins, clearly, and n balls. And what we are doing is chucking these n balls into these bins. So like chuck 1, chuck 2, chuck 3, chuck 4, blah, blah, blah. And after all of the n throws, we ask, what is the expected number of empty bins? Okay, after n throws. Okay. So again, and assuming each throw has equal chance of hitting every bin. Okay. I guess again, first question, what is the underlying, and feel free to pause the video and think about this to the 5 people watching this, but 5 is still optimistic. To the expected 1,000 number of people watching this. See, that's why it's different from what expectation is mathematically. Feel free to unsubscribe. Anyway, so what is the expected number of empty bins? Okay, again, what is the underlying random variable? So we said that there are n tosses, right? Each toss can go into any of the m bins, right? So my random variable is a sequence of n elements, and each element can represent the bin it's going into. So that's the thing I don't know, right? So for instance, maybe B1, B2, B2, B3, B4, B3, B1. Maybe there are 1, 2, 3, 4, 5, 6, 7 tosses. And this is the description of one of the tosses. And this description is the thing that's random, right? And all of these tosses can happen with equal probability. So I guess how many values? So this is the random variable. Maybe I will write this properly. So the random variable is x1, x2, and so on, xn, where each xi belongs to 1, 2, and so on m, right? So how many values can this random variable take up? So for the first guy, there are m possible guys, and then again m possible guys, and so on, right? So it can take up so there are m to the n. Am I right? Yeah, m to the n values. And each of these sequences again occur with the same probability. So m to the n values each occur with probability 1 over m to the n. And again, what is the function we're computing? I wonder whether we can do the same problem from the perspective of the bins instead of just the balls. I don't think so, because every ball is definitely thrown into some bin, but some bins can be empty. Yeah, no, never mind. This seems okay. Okay, so when you take a sequence, so let's just say, example, let's say there are 5 bins. 7 balls, okay? So you can take maybe one of the values that the random variable takes up is 1, 7, 3, 1, oh, sorry, just 5 bins, right? 1, 3, 3, 1, 2, 5. 2, 3, 4, 5, 1. Okay. Now for this random variable, how many empty guys turned up? Just one, right? The only guy we haven't seen here is 4. Every other bin has a ball in it. So this is 1. Okay. So f of x is again okay, I'm going to screw that up if I try to write it formally. But okay, let me write it in words. F of x is number of bins missing in x. Okay. Okay. So, okay. Now, how do we divide this f of x into functions that make expectation of each function easier? We can ask, is for f of x, for this particular sequence of tosses, was 1 empty or not? Was 2 empty or not? Was 3 empty or not? And so on, right? And we can add that up. So f of x is equal to f1 of x plus f2 of x, and so on, fm of x, where fi of x is equal to 1 if I does not occur in x and 0 otherwise, right? And in this case, we have, for this particular example, we have f1 of f1 plus f2 plus f3 plus f4 plus f5, which is f1 is, does 1 occur? Yes, so that's why it's 0. Does 2 occur? Yes, that's why it's 0. 3 occurs? Yes. 4 occurs? No. 5 occurs? Yes. Okay, so 1. Right. So we've divided into sequences like functions like so. And now we can ask, okay, how do we take expectation of these functions? EF1 plus EF2 and so on, EFN. How do I take expectation of this? Okay. Now I'm asking for a particular sequence. I don't want the ball to drop in 1, but to all other possibilities, right? All other possibilities means each element had m minus 1 ways of picking a bin, because it's not allowed to pick the first bin, but can pick everything else. So the number of possibilities are m minus 1 to the n, right? Instead of m to the n. So m minus 1 to the n over m to the n, right? So that's the expectation of F1. And just like last time, I guess this is a big thing, like it's symmetric. There's no reason for the first bin to be different from the second. So the same thing holds for every bin. So this is m minus 1 to the n by m to the n, and so on m times. And so finally, expectation f is m times m minus 1 by m whole to the n. Yep. It's not like as neat as last time. Oh, just one guy gets his hat back. But yeah, that's how you compute it. And I don't know, maybe if we put numbers for our 5 and 7 case, I don't know if we can see something. So for the example case of 5 bins and 7 balls, right? So we have 5 into 4 by 5 to the 7. That seems like a very small number. To the 0.2. Okay. Oh, okay. Wow. That is crazy. 5 into 0.2. 0.2 something, which is 1. So if you drop 7 balls into 5 bins with equal probability, you can expect 1 to be empty at the end of it. And I didn't mean for this to have the same answer as the previous, but yeah, that's interesting. Okay, so now let's do a slightly harder problem, and one which I hope to do justice to. It's called the coupon collector problem. Okay, so what is this problem? So you know how like sometimes when you buy, I mean, a lot of places give the example of cereal boxes. Like I personally never collected this, but okay. So when you have cereal boxes, they sometimes have these collectible cards with them, and you really want to collect the set of all possible cards, and each cereal box just comes with one card, right? So say there are n cards, and you want to collect them all, right? What is the expected number? 1 per cereal box. And of course, if you buy a cereal box and get a card, they won't. No, the universe is not kind enough that when you buy the second one, you won't repeat, right? You might repeat. So, and like each cereal box has equal probability of in getting all the cards. So, what is the expected number of cereal boxes to buy to, I guess, select all? Okay. Right. So again, what is the underlying random variable? What is the function we're computing expectation of? How do we split this function up? Those are the ways we need to think, right? But then when we ask what the underlying random variable is, what is it? You get the first cereal box, there's some random card in there. You get the second cereal box, there's some random card in there. And you keep buying cereal boxes and there's more random cards in them. And this is an infinite sequence, right? So your random variable is x, which is x1, x2, x3, and so on, up to infinity. There's no xn, right? So we are now in the space of infinite sequences of uh, uh, strings where each element is 1 to n, right? And here it's not so easy. First of all, if you take the set of all infinite sequences, there are uncountably infinitely many of them. Oh, I don't know how to say that, but infinity. This is just like real numbers. Okay. And when you have uncountable infinity, things get a little, and it seems like funny that okay, such a simple problem seems like very discrete math. And it is simple, to be honest. Like it's okay. No, okay, that's not fair. It is not simple. I mean, it wasn't simple to me. But okay, how so easily you can, okay, I guess what I mean to say is so easily you can enter, now you have a sample space with uncountable infinite elements in them. And now you need to be very careful with probabilities when you have something like this. Right? Your normal like taking every element and assigning a probability to it doesn't work, because you can imagine, like, if you assigned some non-zero probability to more than finitely many of these sequences, it would, the sum won't be one, the sum will blow up to infinity. So what do we do? I mean, I guess, okay, that's not fair to say. You can assign them. Oh yeah, that's probably not fair to say, because you can, keep decreasing and assign them in different ways. Yeah, you can probably assign them in different ways. That's not fair. That's not fair to say, but the usual notions don't work. For example, if you ask, so like this is studied separately and we need to think about probability a little more, and we need to ask, okay, what is the measure on this space? And I'll just give you some intuition. So for instance, so what we do is, instead of assigning probabilities to single elements of the space, we assign probabilities to sets of the space, and in a way that makes intuitive sense to us. So if you ask, what is the probability of sequence 1 1 1 1 1 1 and so on, that's just like one single point in, like, you can imagine, in this uncountable infinite space, the answer is 0, because we say this is too small of a set to assign any probability to. Whereas you can ask, what is the probability of the set of sequences starting with 1? So it's 1 something something. This is a large enough set. This is an infinite size set. And this has a probability equal to, what is the probability of getting 1 in the first element, which is, out if there are n elements, 1 over n. So the probability of this is 1 over n. Okay. So to make clear, at least for this problem, what we're going to say is, if we have sets that are defined by looking at the first n elements, right? So sets, we know how to assign their probability. That's what we're going to say. We're saying in general, like for like this current session, like in other people know, but for this current session, we're saying we might not know how to assign probabilities of all sets, but we know how to assign probabilities of sets where membership is decided by looking at first n elements. Okay. And that probability is just the probability. That's what we know how to do. That's what I'm claiming. So for example, if I say strings starting with 1 1 or 2 2 or 3 3, right? So what is the probability of getting 1 and 1? 1 in the first element is 1 over n, where we said like each of them have equal probability, right? 1 in the second element is 1 over n, so that's 1 over n square, and each of this is 1 over n square. So this is 3 times 3 over n square. Yeah. The probability of is 3 over n square. So yeah, and I think this is usually the case when we do expected. I'll show you a problem which is probably like a detour which we'll take to solve this problem, which is a standard problem where we are essentially doing this, where we say we don't know how to assign probabilities for all of the sets, but we know how to assign probabilities for the sets whose membership is decided by looking at the first n elements. And maybe that's a good time to do the detour. Detour. And we're doing this detour because we will need it for our problem. And to remind you, the problem was, what is the expected number uh, of cereal boxes I have to buy to collect all the cards in them? Okay. So the detour is this, like, again, a standard problem of coin tosses, where you say you are tossing like a coin infinite number of times, you're allowed to do it. What is the expected number of tosses before you get a heads? And let's say it's a biased coin, where heads occurs with probability p and tails occurs with probability 1 minus p. So what is the expected number of tosses to get heads, right? Now, when you can imagine you get heads in the first try. And notice that when I say heads in the first try, I'm really saying the set of all sequences that starts with an H. And the probability of that set is P. Okay? So notice that this is the same thing what I said before, where we know how to assign probabilities of sequences of sets by looking at the first finite element. By looking at the first n elements or finitely many elements of the sequence to decide membership in the set. Those types of sets we can assign probabilities to, and this is the way we do them. And otherwise, like this problem of like infinite coin tosses and like assigning measures and making it satisfy the axioms of probability is something that you need to study separately, and it's not something that's obvious or something that immediately comes when we do the discrete finite case, I guess is what I'm saying. And then you might imagine where you do a tail and then a head. So this is like the f of all such sequences is 1, right? The function we're trying to compute is number of tosses to get head. And for all such sequence, like maybe if I'm calling, maybe I can say this is x, probability of x and f of x, right? So x is all sequences starting with h, and the probability of that is probability of that is p, and the f of x is 1. All sequences starting with th, the probability of that is 1 minus p times p, and f of x is 2. tth, probability is 1 minus p the whole square times p, f x is 3, and so on. And so on, right? So now we have expectation f, which I'm just going to write as e here, is p plus 1 minus p times p plus 1 minus p the whole square times p. Oh, sorry. 2 times 1 and 3 times this, and so on. And there's a trick here where you just multiply this by 1 minus times and p times e, and you just get 1 minus p times p plus 2 to 1 minus p the whole square times p, and so on. And this cancels this and this cancels this. So you get e minus 1 minus p of e equals p plus 1 minus p times p, 1 minus p the whole square times p, and pe equals p times 1 plus 1 minus p plus 1 minus p the whole square, and so on. And e equals, this is the geometric sum formula, a by 1 minus r, so 1 by 1 minus p equals 1 over p, right? Okay. So what this is telling us is the expected number of tosses to get a head is 1 over p. So for a normal coin, if p is equal to half, you expect to get to do 2 tosses before you you see ahead, and if P equals 1/7, for example, you expect to do 7 tosses. And this, remembering the number of tosses, the expected number of tosses is going to be useful to us. Okay, so that was a little bit about like this sort of how this sample space is actually slightly different from the one we've been dealing with, but that's okay. Linearity of expectation and like and this trick that we have here will allow us not to think about the fact that our sample space is not so nice. But yeah, the important thing is like when we did the proof above, we did it for discrete random variables, but that also holds for this continuous case as well. Yeah, that's important. This linearity of expectation thing. The same thing would hold with integrals. So now, where are we? Yeah. So we said we have these random variables which are infinite strings. And so let's do an example that's easy. So let's say 7 cards, and you might have a string like 2 2 2 3 4 1 1 1 2 3 7 5 1 2 3 4 5 6. Okay, and so on, continuing. Okay, so for this particular sequence, let's say for one value of x, so this is x, and for this value of x, what is f of x? So f of x is the number of cards I needed to, the number of boxes I need to buy to see all n cards. So I see one card here, I see my second card, I see my third card, fourth card. This was a repeat, useless. This was a repeat, useless. Fifth card, sixth card, seventh card, right? So by the time I saw my seventh card, it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So f of x is 14 here. Okay. And maybe f of x is, just writing here, number of yeah, how do I write this? Number of elements for all cards to be seen. Okay. And this is equal to 14. Okay. Now, let's see. How do I break this up into something that's, I definitely can't do linearity of expectation because I cannot do these uncountable infinite things and they're going to be confusing. So how do I break this function up into smaller functions whose expectation I can compute? And I feel like this breaking up is super clever. You can break it up as follows, where f1 of x is elements to see first card. f2 of x is elements, number of elements, I guess. Number of elements. Just ensure it's recording. To see a first card. Number of elements to see second card. Assuming first scene. Okay. And f3 of x, again, number of elements to see third card, assuming first and second scene. And the cool part about the way the functions are split is you don't care what the cards are, right? And this is important because later when you're computing probabilities, we notice that it doesn't matter what the cards are. And maybe to make that clear, let's see what these look like. So what is the number of cards for this particular okay. So, okay. So for this particular sequence, what is f1 of x, right? How many cards did I need to get my first unique card? Clearly one, and it's always one for every single sequence, right? Because the first card you see will be a new card. So f1 of x is 1. f2 of x, assuming I saw my first card, how many cards did I need to see my next one? So I count that. Then I needed 1, 2, 3. That's when I got to my new. So f2 of x is 3, right? Because that's when I saw my next new one. And then f3 of x is 1 again, because I saw my next new one. f4 of x is 2, oh, 1 again, because 1 is new, right? f5 of x is 2, 3, 4, 5. f6 of x is 1 again, and f7 of x is 2. And if I add them all up, I get 1, 2, 3, 4, 6 plus 5, 11 plus 3, 14, right? Which is this. Okay, right? So this, notice what these functions are, and notice that I can compute the value of, say, f3 of x for all of the x's without worrying about what the previous cards seen were. Like, so for instance, if I have another x, like 1, 2, 3, right? Here, f3 of x is 1 for this, because after seeing two cards, how many steps I needed to see the next one was just 1. So these are all functions. f1, f2, fn are all functions defined over the random variable x, where I just look at the random variable and I can check that sequence, right? Okay, awesome. So now we have we have a random variable, we have a function, we have the functions we've divided into, and all that remains is find the expectation of our little functions. Okay, fine. What is yeah. What is the expectation for f1? Okay, we know that for every single guy in the set, f1 is 1 exactly. So clearly for us, I mean, to tell it in like uh, the way we might say it is, for a set of probability 1, clearly all of them would start with the function takes value 1 for a set of probability 1. Okay, so e of f1 is 1 times 1, because the value is 1 and the probability with which this is taken is 1. So this is 1. Okay, that is cool. What is e of f2? Now, how do we compute f2? We know that once f1 happened, there's one card that's taken, right? So we only want one of the other n-1 cards to occur. So it might be that we hit jackpot in our first go. So something that we like occurs. And let's just call the things we like as H and the things we don't like as T. So maybe in the first go we get H, right? And then that would be like, so for all the sequences, for the probability of all sequences that start with this guy, the function would be 1. Then you have a TH, you might get a TH, or maybe I should make this clear. This is, I don't think very clear. Okay. So okay, what was function F2? F2 was having seen one of the cards. What is the expected number of, okay, this is what is the expectation of F2? What is the expectation of the number of cards you need to see the next guy? And the next guy is any of the other n-1 cards, okay? So let's say that, so what are the possible sequences? Like the first chance itself, you see the next guy. So, and here I'm calling H is the favorable, or maybe I'm explaining it the same way, probably. Hopefully repetition helps because I haven't improved the explanation. Unfavorable. So what are the possibilities of F2? So if you hit H first, the value of F2 for all these sequences is 1. If you do a TH, the value of F2 for all these sequences is 2. If you do a TTH, so unfavorable, favorable, favorable, it's 3, and so on, right? And we just computed we literally just computed the expectation for such a function, which takes values 1, 2, 3 for, H, TH, TTH. And in this particular case, the probability of H is n-1 over n, right? Because any of those n-1 would be successful. And the probability of T is 1 over n. So EF2 is from our from the coin toss question, the expected number of coins to hit heads is 1 over P, which is n by n-1, right? And similarly, if you ask what is EF3, EF3 is pretty much the same thing, except now you've already seen 2 cards. So your probability of success is n-2 over n, right? So EF3 is again 1 over P, but this time P is n-2 over n, so it's n by n-2, and so on, right? Until you get to EFN, which is the nth card, which you will only see with probability 1. Sorry, you will only see with probability 1 over n, so it is 1 by 1 over n. So E is n by 1, right? Okay, so these expectations were easy enough to compute. And so we finally have expectation F is expectation F1 plus expectation F2 and so on, expectation Fn, which is 1 plus n by, so I guess I can write this as n by n plus n by n-1 plus, or maybe n by n-2 and so on, or maybe a better way would be to write this as n1 plus 1 by 2 yeah, 1 by 3 and so on, up to infinity. And this is the harmonic series, and this one's sum has been studied. And this sum up to n, and we care only up to n, like the number of cards at least is finite. We haven't been asked to luckily collect infinite cards. Good thing that's not the problem. So so it is enough for us to sum up this thing up to n. Right? And this thing approximately sums to ln n plus gamma, where gamma is 0.577. So is equal to n ln n plus 0.6. Okay, roughly equal to. So yeah, and it's pretty surprising, right? You wouldn't expect a log factor here. And if someone just like asked the question, there's of how many cards you would have to collect, there's no way I would have come up with like, this expression n log n. But yeah, it turns out that is the answer. And I guess if we want to put in some numbers, if you need to collect 30 cards, then you have 3.4 plus 0.64. So 30 into 4. 30 into 4 equals 120 cereal boxes. Not too bad. Yeah, to the extent that expectation refers to your expectation. Yeah. Yeah, so that is the 3 problems on linearity of expectation. So I feel like it's very nice and easy to have a model, but so now I'm going to try a problem that I might have tried before a long time ago, but I don't remember it at all. So, and I'm going to apply what we did here. So let's see if this whole underlying random variable thing idea actually helps, or it only helps in hindsight once you know solutions. So I'm going to, so this is a problem which I just searched some coding problem on linearity of expectation and I came across over. Maybe I need to find it. Okay, I need to search for it again. I lost it. And I found this problem on AtCoder that is supposed to be a linearity of expectation problem. So we will now switch to the usual sides where my journal goes this side and this problem goes here. And let's see if these ideas help or whether they're useless. Yeah, you should see my screen. And I also need to change my, well, maybe I'll stop sharing for a second. Okay. Stop. Okay, so I'm going to be trying this problem that is supposed to be related to linearity. Okay, there are n dishes numbered 1, 2. Okay, I need to orient myself to solve this. 1 to n initially for each I. Less than equal to n. Dish I has each I dish I has AI1 less than equal. Okay, 3 pieces of repeatedly until all the pieces. Roll a die that shows numbers 1, 2 to n with equal probabilities. Let I be the outcome. If there's some pieces of sushi on dish I, eat one of them. If there is none, do nothing. Find the expected number of times the operation is performed for all the pieces of sushi are eaten. Okay. So there are n plates. Each of them has some AI pieces of sushi on it. We roll a die. We hit a plate. And if there is something, we eat that. If there is none, do nothing, and then roll again, right? The expected number of times the operation is performed before all of it is eaten. I see. Right. So yeah, here clearly, I mean, it's very clearly the last, similar to our last problem, right? Like the underlying random variable is the die rolls, and there are these infinite so in a set of infinitely long sequences, and that is an uncountably infinite set. And for each sequence of die rolls, yeah, in dishes 1 to n. So yeah, the yeah, are the die rolls. And so an example die roll, example element, example value of random variable is say 1, 2, 2, 3, 2, 4, 2, 1, 2, 4, 3, and so on, right? And if there are some pieces of sushi on dish I, eat one of them. If there is none, do nothing. Right. So for this particular sequence, the function that I'm computing, right, is how many elements do I need to go down the sequence before I've touched the ith plate AI times, right? So since there are, so so the first plate, how many times do I need to roll this such that the first plate I see A1 times, and the second plate I see A2 times, third plate I see A3 times, and so on, right? Within the roll. Okay. Find the expected number of times the operation is performed before. Yeah. So that is the function we're computing for a given role. How many before I've seen everything. And yeah, so I guess this is in fact very similar to the coupon collector problem. However, instead of saying n cards, it's like saying card 1, I want 3 off, card 2, I want 2 off, card 3, I want 4 off, and so on, right? So like now I'm looking at, so I can imagine that I have the number of functions. So the number of functions I have is actually sum over IAI, right? Because those are the total number of cards. And I can say my FI is like number of elements before I see in order to see a useful element, right? And to see a useful element, because so for example, if dish 3 had 3 pieces of sushi, 3 3 3, I would have f1 equals 1, f2 equals 1, f3 equals 1, because all of those were useful elements. Yeah, number of elements to see a useful element, and the expected number of times the operation is performed for all pieces of sushi are eaten. And this is essentially um, okay, it's not that obvious because, oh, can I just do this? No. Okay, I like this question. It's sufficiently similar, but sufficiently different. So, okay, going back. Again, underlying random variable are these die roles. There's a long stretch of them. The function we're computing is, again, to see like the least number of elements I pass such that each of the ith elements have been seen AI times, right? At least AI times. And now the question is, how do I split these into smaller functions such that expectation of the smaller function is easy? And let's say the first one is obviously useful. Okay, f1 is 1. Let's say the number of times I saw the first guy. F2 is number of times, expectation of is seeing another useful guy. What is the probability of success for 2? And does it depend on what I saw for 1? I guess that's the question. Yeah, I think it does. Depend on what I saw for 1. Because let's say, okay, let's take a simple case where each plate has just one guy on them. Then perfect. Everything I'm saying holds. It's exactly the coupon collector problem. But now, let's say the first guy has 2. Then the probability for this is also 1. No. Yeah, sorry. Maybe I should make myself clear. Let's assume the first plate has 2 pieces of sushi. Oh, wait, I don't think I'm sharing the rights. Okay. 2 pieces of sushi, and then the rest have 1, right? So if my first element is 1, then my second element can be anything. So P of success is 1. However, if my first element is 2, P of success is n minus 1 over n, right? So it's not useful to split it into functions like that. Okay. Mhm. You want to split it into like these independent functions that aren't related to each other. That would be good. It would be hilarious if this wasn't a linearity of expectation problem and there's like an easy way to do it that I don't see. Yeah, and I think this was the educational DP contest, so it's probably some DP thing too. Okay. Oh, can I just change the weight of the die? Like, I don't know if that's equivalent. Like, if you have more pieces of sushi on it, just say that there's a success with higher probability there. I don't think that's useful. Uh, Yeah, I'm giving myself at least 10 minutes to think. Yeah, so the having different pieces of sushi is what's making this not independent. Or does that not matter? Is that why it's a DP problem? And it's like really small values to 1 less than equal to n less than equal to 300 and 3. I can even do like an n cubed solution. Ooh, n cubed. AI is 3. So, okay. Um, okay, how would I do that?
Mm. Maybe I can do this. Oh, one second.
Okay. What if I say it's okay that the functions depend on each other? But let's see what happens. Can I draw a tree? So EF1 is equal to 1 always. Okay, let's say EF1 equals 1. And then based on which of the n guys I pick, EF2 is the remaining probability, right? And again, based on what I pick amongst what is left, I have EF3. And each of these branches it's confusing. Yep, I think I'm going to, yeah, it's been 15 minutes. I think I'm going to call it a day. So I wasn't able to solve this, but I think at least I understand the framework. Maybe I will either make another video attempting this or just think about this. Yep, so that's all for linearity of expectation. See ya.